Okay, let's start our Introduction to Robotics course with a brief look at automation, where robotics fits within the production environment, the industrial environment, the manufacturing environment, the different types of automation. We'll look at some examples of these, and then we'll also talk a little bit about the course and what you can expect going forward. So the objectives of this lecture are going to be a look at industrial automation types. Also, we're going to talk about different types of robots because there's lots of different types of robots. We're going to talk about some different robot configurations and look at some different robot configurations, and then some of the applications that we find robots in industrial or production or manufacturing environments. So first of all, let's talk about automation. There's three basic types of automation, okay? And when we talk about automation, what we're talking about are automated processes that are done with very little or no human assistance, okay? So anything in a production environment, anything in a manufacturing environment that is done automatically without a human interfering or assisting, or if they're assisting, there is very little assistance. Okay, so that's what automation means in a industrial production environment. The three types of automation are the hard or fixed automation, soft programmable automation, or flexible automation. Okay, when we talk about hard or fixed automation, what we're talking about is our machines that are specifically designed for a certain task, and they really can't be changed. Okay, they're custom made to perform that task within that kind of context or within the scenario that they're in, and they can't be switched or reprogrammed. Okay, and hard or fixed automation is not programmable, generally speaking. Okay, so it's just going to do one thing over and over again. Soft or programmable automation is where we have machines, automation that is able to accommodate a variety of product configuration, right? We can make different things, and typically that's done by reprogramming the automation equipment. Okay, so this may include robots, obviously, but it doesn't have to. There's other kinds of automated equipment that are not robots that are programmable. And then the third type of automation is flexible automation. And this is kind of a type of automation between hard and soft automation. So it kind of fits, you'll see in the next slide when we look at where they fit within the production environment. Flexible automation is going to be typically able to be programmed, but again, it doesn't have to be programmable. But we can do a few different things with this flexible type of automation. Okay, so let's look and see where they fit within the production environment. Okay, so on this chart here, we have on the x-axis, we have product variety. Okay, so this means the number of different products that we can manufacture. Okay, so on the left-hand side of this, we have very, very limited number of products. Think in terms of like a blacksmith, right? A blacksmith can only make certain things, right? Not a whole lot of variety there. Maybe 3, 4, 5 different things that you can actually make with blacksmithing, right? Old school blacksmithing, versus going up to a product variety in the thousands, right? So is it a production environment where we can make just about anything we want to make? Okay, so we have a great variety of products that we can manufacture. So that's the x-axis. On the y-axis, we have production volume. That is how many parts we make per year. Okay, so again, we can talk about a blacksmith, right? How many horseshoes can a blacksmith make per year? Well, you know, since each horseshoe is going to be custom made to that horse, you know, the ability to make a lot of parts per year is going to be very limited, right? So it's going to be on the lower end of this versus some kind of a CNC machine or very fast automation where we're making a lot of parts per year. 15,000, like a sheet metal stamping operation, we can make lots and lots of parts per year. We could also say like plastic injection molding. Those parts can be made very, very fast. So we can make thousands of parts per year there. Okay. So you can see where fixed, flexible, and soft automations fit within this realm of product variety versus production volume. Okay. So when we have a very high production volume, but we don't have a lot of product variety, then that's a perfect case of when we would use fixed automation. Okay. So again, an example of fixed automation would be maybe a conveyor belt, right? A conveyor belt is going to go from point A to point B, and there's not really an opportunity to go in different directions with that, at least in a traditional conveyor belt. Another example of fixed automation would be, as I mentioned, the plastic injection molding machine. Okay. So those dies are going to be pre-formed for that shape that we want to mold. And there's no variety that we can have in that. It's got to make those cups or those dishes or those plates, whatever the plastic shape is. But it can do that over and over and over again very rapidly. So that would be an example. Those are examples of fixed automation where we have a high initial investment for custom engineered equipment. Okay. Custom parts, custom equipment, but we have very high production rates. Okay. Very, very rapid. There is an inflexibility of equipment to accommodate product variety. All right. Moving down to the programmable or soft automation. All right. An example of this would be, a perfect example would be a robot, or we might even say a CNC machine tool. Okay. So a CNC machine tool, we can program it to make any part that we want to. Okay. We can use different metals. We can make large parts and small parts. All right. So a CNC machine tool would be an example of a programmable or soft automation. We can make hundreds, thousands of different parts, variety, but it's going to take time. We have to reprogram it. We have to, train the operators. We have to do all the testing on it. So our product volume is going to be very low or relatively low. Okay. So in soft or programmable automation, we have a high initial investment in the general purpose equipment, right? A CNC machine tool, a robot. Those are relatively expensive, tens of thousands or hundreds of thousands of dollars, right? We get lower production rates, but their flexibility allows us to deal with product variety. We can make a number of different parts, different metals, different shapes, whatever we want to do. Okay. And they have a high suitability for batch processing. So batch processing is when like a production environment is going to work on, let's say we're going to make, this widget. We're going to make this, for the first week, right? We're going to work on the widget for a week, and we're going to make as many widgets as we can for a week. And then we're going to switch and we're going to make another type of widget. All right. And we're going to make that second type of widget for the next week. All right. Between the two widgets that we're making, there may be reprogramming that's necessary. There may be training, testing. There may be setup that we have to do. Okay. That's an example of batch processing where we set up a machine tool, for example, or a robot, whatever we're setting up, programmable automation, so that we can work for a set period of time to produce a number of parts, and then we're going to switch everything and make another batch of parts. Okay, so soft or programmable automation is highly suitable for batch production. And then we get into the middle ground, right? The middle ground is flexible automation, right? So we still have a high initial investment in custom engineered systems, right? We have continuous production of variable mixtures of products. we have medium production rates, but we still have flexibility to deal with product design variations. Okay, and you can notice that robots fit kind of within the soft, programmable, and flexible automation. Okay, in the case of industrial robotics, like the 5-axis robot or the 6-axis robot, there are limitations to how they move and how they can be used. So they're not fully soft or programmable. The robot doesn't move, right? The robot can only do certain things, right? The size of the robot may limit it to what it can lift or what it can do, the speed of the robot. All those things play a factor in that. And so that's why robotics actually spans both flexible and soft or programmable automation. All right. Those are the different types of automation. It's important to remember that as we increase flexibility, that is the ability to make different products, different varieties of products, we're going to move from fixed down to programmable automation. All right. And as we want production to start increasing, as we want to be able to make more parts faster, we're going to move the opposite direction from programmable automation up to fixed automation. All right. Now, the video that we're going to look at now, okay, is going to give us an example in a single production line. We're going to see an example of both fixed automation and flexible automation, programmable automation, right? It's kind of fuzzy, the difference between flexible and programmable automation. But I'll point out the different areas where we can see fixed automation and then flexible or soft programmable automation. Just a little heads up on this. What we're making in this production environment, they're filling tubes with a liquid. Okay, so they kind of end up looking like toothpaste tubes. All right, so you'll see them start as hollow tubes, and then they get filled and they get sealed, and then that's it. Okay, so let's look at this environment. All right, so here we have the operator loading in the cardboard tubes, and you can see in this case right away, the conveyor is going to be fixed automation, right? The conveyor can't deviate from its path that it's set up to. We have different arms. You can see some arms down here. We'll see that one engaged in a little bit to help automatically push this container of tubes down to the next area. So here we have the robot, which obviously has been programmed to do this task. We have end of arm tooling over here to pick up the tubes and place them in the containers. So the robot in this case would be flexible automation, right? It's been programmed, but it does the same thing over and over and over again. As we move through here in the assembly line, you'll see that they're placed in these cup holders or these tube holders, and then they go around. And as we move around here, you'll see more examples of fixed automation, right? So these, we wait for these to get around here. There we go. And I'm going to pause that right here. So you'll see over here, we have the tube filling stations, right? And then over here, we have the, I believe this is where they're crimping the end of the tube, right? And again, both of these are, have examples of fixed automation, right? This is all custom made equipment. We can't switch it to another area. We can't easily change what we're doing on this assembly line. Same thing down here. We have all these custom made pieces of metal that are moving in a custom made kind of orientation. All examples of fixed automation. All right, we'll zoom in here in a little bit and see some more examples. Here you can also see the device that is rotating the tube. And what it looks like it's doing is it's rotating the tube so the barcode can be scanned by the scanning device. All right, so that's an example of more fixed automation. And here we have These, I believe these are going to be for cleaning out the tubes, making sure the tube is empty before. Here's the filling station, right? So we're filling it with a liquid. I believe this is some type of grease, all right? So they're filling it. You can't even see what they're filling. It's so fast, but that's the nature of fixed automation, is that it's very, very rapid, basically as rapid as you can get it. But it's extremely inflexible, right? It's going to do the one thing that it's designed to do and nothing else, all right? And here's the crimping station for crimping the end of the tube, and you can see it's folding it over, kind of like the end of a toothpaste container. Again, an example of fixed automation. Okay. All right, so I think we'll leave this here. All right, so that was just to give you an idea of what fixed, flexible, and soft automation looks like. They're usually an assembly line or a production line is going to have a mix of all that together. Okay, so let's move on. And so we'll talk about robots. So what is a robot? What is the official definition of an industrial robot, or any robot for that matter? A robot is a reprogrammable, multifunctional manipulator designed to move material, parts, tools, or specialized devices through various programmed motions for the performance of a variety of tasks. All right, that's a big definition. So let's kind of break it down and kind of focus on the key elements for that, things that you need to know in order to understand what a robot is and what a robot is not. So first of all, a robot is a machine, all right? That's kind of obvious, but it's important to note that it is a machine that is reprogrammable, all right? Not just programmable, as in you program it once and then that's it, but reprogrammable in the sense that we can program it over and over again to do a variety of tasks, okay? It has a multifunctional, or it is a multifunctional manipulator, or it has multifunctional capabilities to it. You can't see it on these examples, but the end of the robot is really the crucial area, okay? The end of the robot is where we might say the rubber hits the road in terms of what the robot is capable of doing. We call what goes on the end of the robot the end effector, or the end of arm tooling, okay? And like I said, there's none of these robots have anything on the end of it, but that's where we're going to be manipulating whatever we need to manipulate, whether we're lifting something up, whether we're moving something from point A to point B, whether we're doing some kind of operation like cutting or grinding or drilling. It's all done on the end of the robot, on the end of the last arm of the robot. And finally, it's flexible. And by here, flexible doesn't mean that the robot is bendy, right? Obviously, these are made out of steel and iron, and they're not going to be bending whatsoever, and you really don't want them to bend at all. But flexible in the sense that we can ask the robot, we can program the robot to do a number of different tasks. Okay, so we can have a robot that one day is going to be picking and placing things, and next day it's going to be lifting up and holding things for us, and then a third day it's going to be drilling or doing some kind of grinding operation. All right, a lot of times this is done by just changing the end effector, right, on the end of the robot, and then of course reprogramming it. But in that sense, a robot is truly flexible. Okay, so remember, a robot is a machine that is reprogrammable with a multifunctional manipulator, and it's flexible. It's able to do different tasks. All right, so how does a robot operate? Well, there's a number of different ways that we can classify robots. Okay, so this is not the only way that we classify robots, but it's helpful to understand different ways that we can classify a robot. So one way that we can classify a robot is by its control system. Okay, the control system is basically the way that the robot is being controlled. All right, or the way the robot controls itself might be a more accurate term here. So we have non-servo robots and servo robots, and this is This is a servo drive right here. You might be familiar with servos if you've ever played with remote control cars. Remote control cars have servos on them. And basically what a servo is, a servo motor, is it's a motor that can rotate precisely. And what that means is it knows where it's rotating that axle, right? Or that spindle or that shaft. So in this servo motor, this shaft is going to rotate, right? And what's going to happen is the servo motor has a mechanism inside the motor, right in this region right here, so that it can basically count how much that shaft rotates. And that's very important because in a closed loop system, we need to know, the robot needs to know where it's moving to. And it moves by using these servo motors. Okay, so that's what we call a closed loop system. And a closed loop system uses servo motors, so we call those servo robots. Right? The feedback system that we're talking about here is basically the robot is told to move from point A to point B. Right? And in order to stop when it gets to point B, it needs to constantly be asking itself, am I at point B yet? So what happens is we tell the robot to move from point A to point B. It starts moving, and then the robot says, am I there yet? And it checks to see whether it's there yet by checking on how much the shaft on the servo motors rotate. And then if it's not there yet, it continues to move. And it continues doing that until it gets there, and it says, hey, am I here? And it checks the position, and it says, yes, we're there. All right. So that's a servo robot. Closed loop system. Feedback is involved in that. We're going to talk about closed loop systems in a second, but our robot and most industrial robots are servo robots. They need to know where they are. A non-servo robot would be a robot that is, that doesn't know where it is. It just moves. Okay. So let's say, for example, a remote control car. Is a remote control car a robot? Well, it could be a robotic type of car, but think about how does a remote control car, when we move it, how does the car know where it is? Well, it doesn't, right? It doesn't. How do we figure out where the car is? Well, we have to be involved. The user, the driver has to be involved in that by looking and seeing and determining, did the car reach the point where we wanted it to go, and then we can make it turn back. So the car in and of itself does not have any positional knowledge, any positional control. There is no feedback mechanism to send the car out and to have it go back. Now, if it was a programmable remote control car, then we would need to have servo motors or some type of sensory system on the remote control car to tell us when it's reached this point and to send it back. Another way that we can classify robots is by their drives, right? By drives, I mean the motor units that are making the robot move. Robots can be either electrically driven, hydraulically driven, or pneumatic. Okay, hydraulic means it's going to be using oil pressure basically to move it in large pistons. Pneumatic means that we're going to be using air pressure. Typically, pneumatic drive robots are going to be smaller robots. Hydraulic drive robots are going to be larger robots. The robot that we're using in our classroom is an electric drive robot. Okay, so it's kind of the middle ground. All right, so now let's talk a little bit about open loop systems and closed loop systems. All right, as I said, our robot, most industrial robots, are going to be an example of a closed loop system. So let's start off by looking at an open loop system and why we might not want to use an open loop system, and instead opt for a closed loop system for our robot. So an open loop system basically is a device that is going to function for a set amount of time or a set degree or a set parameter, and then it's going to stop. So basically an open loop system, we turn it on, it works until it's turned off. How it turns off is going to be different parameters. Let's say a clothes dryer. All right, a clothes dryer, especially one of the older clothes dryers, is a good example of an open loop system, right? How do we operate the clothes dryer, one of these old tiny clothes dryers? Well, we're going to throw our clothes in, right, into the clothes dryer. We're going to set the time. So let's say we set it for 30 minutes. And we're going to hit the button on the front panel of the clothes dryer. By hitting the on button, we're going to bring in electrical energy and activate the dryer, turn the dryer on. And the dryer is going to heat up. The heating elements are going to turn on through the electrical energy. And the heating elements are going to stay on for 30 minutes, the desired time frame. When that is over, it stops, right? Now, the problem with that is there's no mechanism to determine whether the clothes, in fact, are dry, right? Or, in fact, if they're over dry, if you let it go for too long. So this is an example of an open loop system. There is no mechanism to determine if the clothes, in this case with the clothes dryer, are dry or not. It just turns on for 30 minutes and then it turns off. So in a closed loop system, we might have what's called a smart clothes dryer. So here, the same kind of situation. We take our clothes, we throw them into the dryer, right? Now, instead of setting the time, we set the desired dryness, right? So we say we want our clothes to be, medium dry, right? Medium dry, all right? We're still going to hit the on button, and the energy is still going to turn on the heating elements, and it's going to rotate the dryer. But now, instead of a time frame saying when the dryer stops and the clothes are done, now we have a feedback mechanism. So now we're introducing a sensor, and the sensor is going to be positioned, right, so that it can measure the dryness of the clothes. And so periodically, the dryer is going to get a signal from the sensor. Are the clothes dry yet? No, the clothes aren't dry. So it's going to continue applying electrical energy, keeping the heating elements on, tumbling the clothes. It's going to continue in this feedback loop until finally the sensor senses that the clothes are at the desired level of dryness. At that point, the electrical energy is stopped. The heating elements turn off. The clothes dryer stops tumbling, and the clothes are done. So this is an example of a closed loop system. Closed loop systems always have at least one feedback loop. And the feedback loop is basically the method by which the system checks to see whether it's done or not, whether it's achieved its goals. Now, in the case of a robot, remember that the feedback in the mechanism here is going to be position. It's also going to be speed, right? Because it has to go from point A to point B at a certain speed, according to the program. There's other mechanisms that are involved in that. There's safety mechanisms that are going to tell it if it's collided with something or if there's something in the way. There may be a vision system. So there's many, many sensors that are going to keep the robot moving until it gets to its desired point, or stop it if there's some interruption to that. All right, so that's why a robot is always a closed loop system, or especially industrial robots. All right, so now let's look at some of the examples of the different types of robots. So we talked about hydraulic, electrical, and pneumatic robots. This is an example of a hydraulic robot. Here you can see the hydraulic actuator or the giant ram. It's basically just a piston. This area inside here is going to be filled with oil under pressure, all right? And the ram is going to be activated. The actuator is going to make the arm of this robot move up and down. These hydraulic robots are typically used for heavy machinery. These are large, messy robots, but we can exert a lot of force with the oil pressure, with the hydraulic actuator. An electric robot, like the robot that we're using, most of the robots in an industrial environment are either going to be electric or hydraulic. We have pneumatic robots are used. They're typically smaller robots, right? Because pneumatic pressure used to move things is not going to be as pressure insensitive as like electric or hydraulic, meaning that a robot that is a pneumatic robot is not going to be as stiff. Okay, that's one way that we can explain it. The upside to pneumatic is that they're very clean robots. They're very safe robots. You know, obviously for a hydraulic robot, these robots actually get pretty messy. There's not really a perfect way to keep all the oil off the surfaces. So this would not be a robot that we could use in a clean environment. With the electric robot, we always have to be cognizant of the electrical charge and whether sparks, not these sparks, this is a welding robot, but sparks from the motor are going to be safe. And so in a pneumatic robot, we have a safe operation with a clean robot, and that's kind of where pneumatic robots are going to fit in. But again, they typically are smaller robots. All right, so let's talk about different robot configurations. All right, there's many different styles of robots, ways that we can shape our robots to achieve specific aims, right? So we have the first one up here is called a revolute or articulated robot. Okay, we can have a jointed multi-axis robot here. This is an example of a jointed or multi-axis robot. You can see that it can rotate on the base. This arm can move, this arm can move, and then we have other motions that we can have with more arms here. This is an example of another revolute or articulated robot. This is a SCARA robot. We'll see an example of this. So you can see it can rotate. It can even move up and down if we wanted to. But each one of these arms is going to rotate. Then we have a Cartesian robot. A Cartesian robot is basically going to move in the X, Y, and Z axial directions, right? So you can see this robot here, Cartesian, we can move up and down. We can move this in and out, and we can move this arm in and out as well. An example of a Cartesian robot, and I think we have a video of this, would be a gantry robot, or actually a 3D printer is a really good example of a Cartesian robot. Is a 3D printer a robot? Well, you think of that for yourself. Go back to our robot definitions and see if it fits the definition of a robot and what type of robot it would be. Here we have a cylindrical robot, a little bit less common. And finally, we have a polar robot. Polar robot meaning, specifically the cylindrical robot is going to operate within a cylindrical zone, right? So this arm right here can move up and down, and it can rotate, and this can move in and out. So basically, it can operate within a cylinder. A polar robot is going to operate basically within a sphere. The polar robot is also known as a spherical robot. So it can rotate, this can tilt up and down, and this arm can move in and out. These are less common. Most of the robots that you see in an industrial environment are these three on the right-hand side. The multi-axis robot here, like the one that we're going to be programming, the SCARA robot, and the Cartesian robot. All right, so focusing on each one of these a little bit more, we have the jointed robot, which is also known as a 5-axis robot. Why is it a 5-axis robot? Well, there's 5 axes, right? It can rotate on the base or the waist. That's one. It can rotate here at the shoulder, that's 2. It can rotate here at the arm, that's 3. This arm can rotate itself, right? And then we have the hand out here. This is called the hand, and that can rotate. So that's 1, 2, 3, 4, 5 axes, right? The work environment is going to look something like this. In a side view, you can see the robot can reach all of this gray area here, but not outside the gray area due to hard limits in the shape, or software limits where we set where we want the robot to move. And then in the top view, we can see the robot can swing all the way around almost 360 degrees. It looks like there's maybe about 45 degrees that it can't go through. So 315 degrees of rotation, something like that. Moving on to a SCARA robot. A SCARA robot is kind of that perfect example of flexible automation that's really, really close to fixed automation. All right. The work envelope for a SCARA robot is much more limited. You can see that it can't really, the blue area is the base of the robot, right? So a SCARA robot can't really move much outside of its base, outside of its own shape. But what it can do is it can move very, very fast, right? And it can do very limited motions very, very fast. All right, so I have a video of a SCARA robot, so we're going to have a look at that right now. So here's a FANUC SCARA robot, and you'll see basically all the SCARA robot is doing in this example is moving these numbered or these lettered discs from one area to the next, but it moves lightning fast. All right, so you can see in this example, the SCARA robot isn't moving with a great deal of flexibility or distance. Its work envelope is rather limited, but it is able to fly in its motions. So it's very fast, it's very controlled. It's also very stiff, which is important, right? It's not flexible, which is good. When you're moving at a high speed, you don't want a flexible robot. A flexible robot at high speed is going to introduce a lot of imprecision, inaccuracy in its motions. All right, so there's our SCARA robot. All right, Cartesian robots, right? We talked about these. These are going to move in the X, Y, and Z direction. So the work envelope is basically just a big rectangle. So in a gantry is a type of robot that is going to be used to lift up and move very, very heavy things. Typically, a gantry is going to be located overhead, right? And it's going to assist the workers in moving heavy equipment from point A to point B. This is an example of a smaller gantry. And I have an example of a gantry robot, right? This one is going to be applying adhesive onto this panel here. And you can see, again, this is a good example of where flexible automation, right? A robot, because we can program it to do different things. And we can put different tools on the end of it, the end effector here. But it's flexible automation that's getting really close to hard or fixed automation, because we can't use a gantry robot or a Cartesian robot to do a lot of different shapes. It's basically a planar shape is what we are limited to. So let's look at how this is going to operate. All right, and you can see the motion. Think of the motion of the Cartesian robot here. The motion is basically going to be in the XY plane right now. And when it's going to be, lifting up and moving back down, that's when it's going to be moving the tooling back and forth. Okay, so you can see it laying down looks like 5 or 6, maybe 8 rows of adhesive. This is a programmable robot, right? You can see it has to skip over that area right there. So this is programmed, but it's relatively inflexible. It's relatively what we would call getting near that hard automation. All right, so let's move on. All right, so cylindrical robots, again, here is that work envelope, and you can see how it's cylindrical shape. That's how these robots are named, right? Cylindrical robot has a cylindrical work envelope. And we'll see an example of, actually, we're going to see a number of different examples here. So this is a gantry, right? You can see the crane here in the different axial directions this is going to move. And how it's being used to lift and move heavy equipment onto the conveyor belt. This is pretty close to fixed automation, but it would still be flexible automation in that we can use it to lift up different things from different locations. All right, let's move ahead a little bit here. And we'll move to the cylindrical arm. So now this rotates. It can move in and out, and up and down. Again, it's kind of limited in their motion. So these are relatively specialized robots, staying with the idea of relatively fixed, even though it is flexible and programmable to some extent. All right, I'm going to move forward just a little bit more. And we're going to, this is a little bit about the work envelope. And we're going to look at now a spherical arm robot. These look very similar to a 5-axis robot, right? But we are missing, here, if I go back here and pause it. So notice that we're missing basically 2 axes, right? So we can rotate around the base, the shoulder can rotate around the shoulder, but the arm can only go in and out. All right, so it's not as, it doesn't have as many degrees of freedom as a 5-axis robot. It can't move, so that's why it's tending, these all are examples of robots that are tending more towards the fixed automation realm. All right. So here you can see this operation, it's a welding operation, looks like. So for certain geometry, this is going to be ideal. Again, very stiff, which is good. That's what we want. Here's an example of how it moves. It rotates around the base. It can rotate around the shoulder, and then the arm can move linearly in and out. What they're calling reach. All right, let's see if I have any more. I think that this is a 5-axis robot. Okay, so this is more of the traditional robot that we're going to be programming. So it can move like this. The arm, what they're not showing you right now is the arm can rotate. Let's see if they're going to show that right there. I'm not sure that they're going to show the arm rotating. I guess they're not going to show that. All right. So those are some examples. Like I said, just to paint a clearer picture for you. Now, looking at FANUC robot, FANUC has a number of different robots in these configurations. We get the one type of robot that we didn't talk about here is the SCARA robot, or what looks kind of like a spider robot here, where you get these 3 arms that are going to be moving the end effector right here. These are kind of interesting. And I don't have a video of these, but, you know, I'm sure that we'll talk about them in class. The white robots here are the robots that are food safe. Okay, and so you can see in this, these white robots are going to be specially enclosed so that we don't have any chance of contamination. You know, they also can be used in environments where you have hazardous materials. So that's the white robots. Yellow robots are kind of the standard robots that you see in an industrial environment. Here we have, this is a hydraulic robot. I think this might be the same type of robot. No, this is the type of robot that I showed you in that picture, the hydraulic robot, right? We have some robots that are hanging upside down from gantries, right? So this is actually not a 5-axis, this is a 6-axis robot because this can move left and right on these gantries. So a number of different configurations, a number of different applications. No SCARA robots here. I don't see any. Do we see any here? These are just the name. The one that we are going to be using in here is the ArcMate, right there. That is the robot that we're using right there, the LRMate style robot. It's an industrial robot, right? Smaller, but still capable of doing everything that needs to be done. The white robots, again, safe robots or food safe robots. The one thing that they're not showing in this, and I think this is because the slide is a little old, are green colored robots. So FANUC has robots that are green, and the green robots are robots that are what we call cobots. Now we have cobots we have a Universal Robotics cobot in the room, and basically a cobot is a robot that is capable of being of working collaboratively with a human in the work environment. And it does that by sensing when it touches somebody or something. So one of the green FANUC robots is one of these cobots or collaborative robots, and it can actually sense if it's moving and it touches you, it will stop moving. All right. Just like our universal robot in the lab. All right. And we'll be programming with that. It's a really, interesting kind of, robot and style of robot. All right. So let's look at some special robots now. These are still robots, right? But they are going to be, kind of unconstrained. In many ways, a lot of these robots are going to be moving, right? So moving in the sense of they're changing their location, not just moving their arms and stuff. So we have 3 different types. We have the automatic guided vehicles, or AGVs. We have automatic guided carts, AGC, or smart carts. And then we have sorting transfer vehicles, STVs. You might have seen these, in different commercials or different videos for Amazon warehouses. These are the robots right here that lift up these large stacks of equipment, and they move to the operator or to the person that is sorting these. They move the equipment and then they take it back into the stack. So you can see the grid. So these move on a grid system, kind of like embedded in the ground. They're going to be moving along this grid pattern. Here's another. These are carts that are used. Again, they move along this track, but they're carts that are carrying different auto parts from one area to the next. All right. So where do robots work? Well, in a typical industrial robotic environment, we're going to have what's called a robot cell, or the safety cell. Okay. And that's basically going to be the room or the area where the robot is set up to operate. Okay. It's the complete system that includes the robot, the controller, right? This is the controller, and other peripherals. Peripherals meaning any kind of guarding, right? Here we can see the laser beam walls that are guarding. Here we have fencing that is guarding it. Any type of workpiece setup right? So we have a rotary table here. Here we just have a stationary table. Those are all going to be part of the robot cell. Robot cells are also known as work cells. They always include safety features such as the fencing, light curtains, here's the light curtain, and other sensors. They have to be a safe environment for the workers. These are not where cobots work though, okay? So cobots kind of break the whole robot cell idea here. So what are some applications of robots in an industrial environment? Well, lots of things, right? Welding, painting, gluing, applying glue, material handling. Like in this example, we're moving, it looks like bags of soft goods. So we have an end effector here that has this kind of gripper. It's going to move down, it's going to pick up a bag, and it's going to place it on a conveyor so it can move from point A to point B. So that would be material handling. We have material removal. Material removal meaning the end effector is going to have a cutting tool, a grinding tool, a drill, any kind of tool that we can remove material with, we can cut material with. It can also be used for assembly and inspection. So we can put cameras on the end of this so that the robot can see and sense where things are and their shape and their size and what they look like. And we can also use robots to put things together. So this is a pretty wide array of industrial robotic applications, and it definitely is not conclusive. There's more and more things that people are coming up with for using robots. So here's some lists of top applications that I found for different common industrial operations. So top 10 applications for robots, right? This is from 2017, but I don't think the year really matters. So top applications, palletizing, that is stacking and unstacking things that are on pallets. This is especially important because pallets are heavy. Pallets can be dangerous, right? And a robot is a perfect opportunity to take a human out of that dangerous, heavy environment and use a robot. Case packing, loading and unloading, smart carts, what we saw back before in Amazon, that's actually the 4th highest application for robots. Material handling, roll handling, board, so assembly, robotic labeling, material handling. Now, in an aerospace environment, all right, the number 1 application is for non-destructive testing and inspection. So we use a robot to test to see whether or to inspect parts. Then we have drilling and fastening, welding, sealing, dispensing, automated fiber replacement. And then in an automotive applications, the number 1 application for robots is painting. And then next to that is welding, spot welding, right? Assembly is another one. Material removal, and then part transfer and machine tending, or moving parts from one machine to another. All right, we're going to finish up with some videos here, just showing some different applications of robots. All right, so here is these are called sizzle reels. Oh, by the way, these are you might have seen a snapshot of. Yeah, here's the spider robots. And you can see they're using vision, right? So they're identifying parts and putting them on in different areas. I'm not quite sure what the criteria is that it's looking for. All right, so those are neat devices, neat robots. All right, so let's move on to the next one here. All right, so here we have robots just showing different applications. So here's a robot doing arc welding. We have material handling where it's picking up parts moving them from point A to point B. Oftentimes these parts are heavy or cumbersome parts, very large parts. This is cutting. That was cutting. I think this is just moving through different motions. Here we have picking up zip ties. You can see the end effectors are, there's a variety of end effectors, plasma welding. All right, so this is an interesting application where we're using the robot to move the workpiece over a sander. So again, we can program that motion so that we get very good consistent results. All right, we're going to move on here. So the course overview and goals for the AET 110 course. This course is intended for an operator, technician, engineer, or programmer who must set up, record, and or troubleshoot programs on a handling tool software package. Okay, handling tool is the name of the software that FANUC uses to program robots that are going to be either doing material handling or any type of tool handling operations. Okay, so in this course, you're going to learn how to program the robot and make it move through different kind of procedures and protocols. We're going to understand how the robot operates and how we maintain a robot and how the safety features of the robot interact with its operation. So when you finish this course, you're going to be able to do all of these following operations. These are taken from the FANUC guide. One of the real benefits about this course is that at the end of the class, you will be certified as a FANUC handling tool programmer and operator. And so that's a certificate that you can put on your resume, and you can show potential employers that you've earned this and that you meet the criteria that FANUC sets for their operators and programmers. Okay, the course that you're going to be doing here is going to be following the FANUC handling tool operator and programmer course. So it's going to be the same thing as you would see if you were taking the FANUC course. All right, so that's the end of this presentation. I hope you enjoyed it, and I'll see you in the next presentation.